A pleasant day, everyone. We are the Group 6 and we will discuss the topic about motion of charged particles in magnetic field. So here are the presenters and members of this group. Starting with Solon and Figueras are the presenters and the other members are already given. So the lesson objectives for this topic is that we will describe the motion of charged particle in magnetic field in terms of speed, acceleration, cyclotron, radius, cyclotron frequency, and kinetic energy. And also we'll be able to evaluate the magnetic force of an arbitrary wire segment placed in a uniform magnetic field. So this has been already learned about the interaction of electric and magnetic fields as well as the motion of charged particles in the presence of both electric and magnetic fields. We have also deduced the relationship of the force acting on the charged particle, which is given by Lorentz Force in this instance. We've also learned about the magnetic force acting on a current-carrying conducting rod when it is exposed to the magnetic field. So what is electric charge? So electric charge is a fundamental feature of matter carried by some atoms and molecules that determines how they react to an electric and magnetic field. Electric charge is a basic physical property of matter that causes it to experience a force when kept in an electric or magnetic field. An electric charge is associated with an electric field, and moving electric charge generates a magnetic field. Combination of electric and magnetic fields is known as the electromagnetic field. Interaction of the charges generates electromagnetic force, which is the foundation of physics. So what is magnetic field? A magnetic field is a location in space near a magnet or an electric current where moving electric charge forms a physical field that exerts force on another moving electric charge. So magnetic fields lines with similar rules are the direction of the tangent to a magnetic field line at any point gives the direction of B at that point, and also the spacing of the lines represent the magnitude of B. The magnetic field is stronger where the lines are closer together and conversely. So now we have learned about the interaction of electric field and magnetic fields, as well as the motion of charged particles in the presence both of electric and magnetic fields. We also know the relationship of the force acting on a charged particle, which is given by Lorentz Force in this instance. Remember that in physics, the Lorentz Force is the combination of electric and magnetic force on a point charge due to electromagnetic fields. We've also learned about the magnetic force acting on a current-carrying conducting rod when it is exposed to a magnetic field. So when an electric charge is placed in a magnetic field, the electric charge will experience a magnetic force provided two conditions are attained. First, the charge must be in motion because no magnetic force will act on a charge at rest. Second, the velocity of the charge in motion must have a component perpendicular to the direction of the magnetic field. So magnitude and direction of magnetic fields are considered to be constant, pointing to the right. So letter A or the table A, a charge moving parallel to the magnetic field B. So in the table B, a charge moving perpendicular to the magnetic field, and the letter C, a moving charge whose velocity makes an angle not equal to 0 with magnetic field B. So the magnitude and direction of magnetic fields are considered to be constant, pointing to the right. So A, in the first figure, the charge moves parallel or anti-parallel to the field. In this case, the charge does not experience any magnetic force. And the letter B, here in the second figure, the charge moves perpendicular to the magnetic field, so it experiences the maximum magnetic force possible. And to the last figure, the charge is moving at an angle with the magnetic field, so the velocity component of the charge, which is perpendicular to the magnetic field, will give rise to the magnetic force on the charge where the force is smaller than the maximum possible force, and the component of the velocity parallel to the magnetic field will yield no magnetic force on the charge. It can also be seen that the direction of the magnetic force is perpendicular to the both magnetic field B and the velocity. So Fm is perpendicular to the plane defined by V and B. So we can utilize the right hand rule to remember the direction of magnetic force on a moving charge or the RHR. So if you extend your right hand so that the fingers point along to the direction of the magnetic field B and the thumb points towards the direction of the velocity of the charge, the palm of the faces the palm of the hand faces the direction of the magnetic force Fm that acts on a positive charge which seems to be push positive charge in the direction of the magnetic force Fm. So for a moving negative charge, the direction of magnetic force is opposite that which is predicted for a moving positive charge. So what can be done to determine the magnetic force on a negative charge is to assume that it is positive and then using RHR. So find the location O the magnetic force or a positive charge and then reverse it to find the direction the force acting on the negative charge. So the magnetic field at a point in space is defined as B is equals to F over current 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 or theta times V sine not equal to zero. So the SI unit for magnetic field is T Tesla. So where F is the magnitude of the magnetic force on positive test charge and V is the velocity of the charge that makes an angle with direction of the magnetic field. So sample problem. So a proton from rest from the positive plate of capacitor, it is accelerated by the electric field towards to the negative plate. So the potential difference between the plates is 2,400 volts. The proton leaves the capacitor through a small hole in the negative plate. It travels at constant velocity outside the plate and enters a region of constant magnetic field of 0.10 Tesla with a constant velocity. Given the velocity at the magnetic field are perpendicular to one another, find the velocity of proton and the kinetic energy of the proton due to the magnetic field and radius the circular path, where the charge of a proton is equals to 1.66 times 10 to the raise of 27 and negative 27 kilograms. So given is the PD between the plates of 2,400 volts and the B is equals to 0.10 Tesla. So requires to find the velocity of protons. So B is the kinetic energy key of the protons due to the magnetic field and the C is the radius of circular path. So solution, so the key is equals to I. So the energy of a proton, EV is equals to 1/2 mv squared is converted to KE. So EV times 1/2 mv squared, then square root of 2 EV over IN, and square root of 2 times 1.6 times 10 raised to the power of negative 9C times 2,400 volts over 1.6666 times 10 raised to the power of negative 27 kilograms. So 6.8 times 10 raised to the power of 5 raised to the power of 5 meter per second is the answer. So letter B, KE is equals to EV does not change. So KE is equals to 1/2 mv squared, and 1/2 mv squared times 1.66 times 10 raised to the power of negative 27 kilograms is equals to 6.8 times 10 raised to the power of 5 ms squared per squared. A meter per second squared rather. So the answer is 3.84 times 10 raised to the power of negative 16 joules. So letter C, radius is equals to 1.66 times 10 raised to the power of negative 27 kilograms times 6.8 times raised to the power of 5 meter per second over 1.6 times 10 raised to the power of negative 19. So the answer would be 0.071 meters. Description of the motion of a charged particle in a magnetic field. This figure shows positively charged particles traveling perpendicularly to a magnetic field. So So a positively charged particle initially travels at right angles to the magnetic field. When a positively charged particle enters the magnetic field, its velocity is also right angles to the magnetic field's direction. Due to magnetic force it encounters in the field, the change is redirected upwards. So as the charge moves upwards, the direction of the force changes. Note that the direction in the magnetic force always remains perpendicular to the both magnetic field and the velocity. The traveling charged particles is unaffected by constant magnetic field. This is because the direction of magnetic field is a force acting on the moving charge is always perpendicular to the charge motions. So as a result, the magnetic force is unable to modify the charged particle's kinetic energy. So this force can just change the direction of the particle's motion. So the particles, so the charged particle in motion in magnetic field has a circular trajectory. So the magnetic force remains perpendicular to the velocity in the field and is directed toward the center of the circular path. So we can find the radius of the path by using the concept of the centripetal force. So what is centripetal force? Centripetal force is a net force on an object moving in a circle which is directed toward the center of the circle. This is the force needed by the object to move along a circular path. So the magnetic force always remains perpendicular to the velocity directed upward toward the center of the circular path. The centripetal force depends on the magnitude of the speed, mass of the particle, and the radius of the circular path. So the magnetic hmm? Oh, sorry. So the equation form is Fm is equals to ma, but a is equals to v squared over radius. Thus, Fm is equals to mv squared over radius. So the magnetic force creates centripetal force which keeps the charged particle traveling in a circular direction. As a result, the magnetic force does not work on the chain charge to maintain it moving in a circular course.
The force on a current carrying wire in a magnetic field. We already talked about a charged particle traveling in a magnetic field that is subjected to a magnetic force, and an electric current is a collection of moving charges in a current wire. A current carrying wire can feel magnetic force because an electric wire is a collection of moving charges in a current wire. When a current carrying wire is placed between the poles of a magnet, it will be subjected to a magnetic force. A current is carried by the amperes wire. The bottom portion of the wire is perpendicular to the magnetic field B in the illustration. The wire is deflected to the right by a magnetic force F. The current I is represented to be clockwise. Therefore, the moving charges are subjected to a magnetic force, which pushes the wire to the right. Instead of using the direction of positive charge to calculate the direction of the magnetic force, using the RHR, we utilize the direction of the conventional current I. The direction of B in the figure is downward, but the direction of current I is toward the reader. As a result, the force acting on the current carrying wire is directed to the right, and the wire is deflected to the right as well. The wire will be deflected to the left if the current direction is reversed. The magnitude of the force that acts on the charges moving through a magnetic field is F equals QVB sine theta, where Q is the initial charge, V is the velocity, and B is the magnetic field. We'll express this in the form we'll need for an electric current now that we're utilizing a current carrying wire F equals QVB equal sine theta T over T. F equals QVT B sine theta over T. F equals ILB sine theta. If the wire has a length L that carries a current I, the magnetic force exerted on this length of wire is the net force acting on the total charge Q moving in the wire. If the time required or the charge to move through the length L, the wire is T, then F equals QVB sine theta T over T. F equals QVT B sine theta over T. F equals ILB sine theta. where Vt equals L and Q over T equals I. Therefore, the magnetic force on a current carrying wire of length L is F equals ILB sin theta. The right hand is orientated with the thumb pointing in the direction of the eye. The extended other fingers pointing in the direction of the magnetic field B, and the palm of the hand pointing in the direction of the force on the wire while using the RHR. Sample problem. An electric power line carries a current of 1,200 ampere in a location where the magnetic field of the earth is 4 times 10 to the power of negative 5t. The line makes an angle of 60 degrees with respect to the field. Determine the magnetic force on 100-meter length of the wire. Given I equals 1,200 ampere. B equals 4 times 10 to the power of negative 5t. L equals 100 meters. Required to find Fm. Solution. F equals ILB sin theta. 4 times 10 to the power of negative 5t times 1,200 amperes times 100 meters sine 60 degrees. The answer is 4.16 N. Key points. The force on a charged particle due to an electric field is directed parallel to the electric field vector in the case of a positive charge and anti-parallel in the case of negative charge. It does not depend on the velocity of the particle. In contrast, the magnetic force on a charged particle is orthogonal to the magnetic field vector and depends on the velocity of the particle. The right-hand rule can be used to determine the direction of the force. An electric field may do work on a charged particle while a magnetic field does not work. The Lorentz force is the combination of the electric and magnetic force, which are often considered together for practical applications. Electric field lines are generated on positive charges and terminate on negative ones. The field lines of an isolated charge are directly radially outward. The electric field is tangent to these lines. Magnetic field lines in the case of magnet are generated at the north pole and terminate on a south pole. Magnetic poles do not exist in isolation. Like in the case of electric field lines, the magnetic field is tangent to the field lines. Charged particles will spiral around those field lines. That's all. Thank you.